Hello my friends and welcome back to the You Can Do TV channel. At Lisnave Shipyard, 5 bulbous bow replacement retrofits were carried out for Hapag-Lloyd's container vessels: Delaware Express, Colorado Express, Potomac Express, Missouri Express, and Hudson Express. Each retrofit began with the removal of the existing bulbous bow, followed by detailed structural inspection of the hull to ensure integrity. New optimized bulbs were fabricated using precision steel cutting, forming, and welding techniques to meet hydrodynamic design specifications. After alignment, the bows were securely welded to the hull, with careful attention to tolerance and joint quality. Piping, sensors, and cathodic protection systems were reinstalled, ensuring full operational readiness. The retrofitted bows underwent thorough inspection and testing, including non-destructive testing and sea trials, confirming structural integrity and performance improvements. These upgrades enhanced the vessel's fuel efficiency and hydrodynamics, significantly reducing carbon dioxide emissions and operating costs. By implementing these retrofits, Lisnave combines advanced shipyard engineering, precision fabrication, and sustainable shipping practices, enabling Hapag-Lloyd's fleet to operate more efficiently while meeting modern environmental standards. This project highlights Lisnave's expertise in high-value ship modifications and sustainable maritime solutions. Lisnave Shipyard operates as a fully integrated maritime service facility, providing technical repair, maintenance, and retrofitting solutions for a broad spectrum of vessels. The hydrolift system supports up to 8 berths with a combined vessel length capacity of 350 meters, enabling simultaneous multi-ship operations. Dedicated stations for tank cleaning and slops treatment ensure compliance with environmental regulations and safe handling of hazardous residues. The shipyard delivers precise machinery repairs, turbocharger maintenance, and propeller refurbishment, utilizing calibrated equipment and standardized procedures. Steelwork and piping repairs employ advanced welding and fabrication techniques, while surface treatment processes, including anti-corrosion coatings and paint systems, extend hull and superstructure longevity. Environmental management is embedded in all operations, from controlled waste handling to slops treatment, ensuring minimized ecological impact. Operations adhere to international safety and environmental standards, maintaining vessel integrity and operational efficiency. Lisnave's skilled technical personnel and modern infrastructure allow for complex retrofits, full-service maintenance, and precision engineering solutions across cargo, tanker, and specialized fleets. The shipyard's methodology emphasizes operational accuracy, structural integrity, and regulatory compliance, establishing it as a leading provider of technically advanced and environmentally responsible shipyard services. This overview underscores Lisnave's technical capabilities in marine engineering, repair logistics, and environmental solutions, positioning it at the forefront of the global ship repair and maintenance industry. Royal Bulbous is constructing a 750 DWT cement carrier for Taiwanese owner Yuming Marine Transport Corporation, marking its first project for an Asian partner. The vessel is designed for efficient cement transport and will strengthen operational capabilities. Following construction, the ship will undergo launching, entering the water for the first time. This milestone signifies the start of a long-term collaboration between Royal Bulbous and Yuming Marine, combining Dutch shipbuilding expertise with Asian shipping requirements for reliable and high-quality maritime transport. China's first 16,000 TEU methanol dual-fuel container ship marks a milestone in sustainable shipping. Measuring 366 meters long and 51 meters wide, the vessel can carry up to 16,136 TEU. Equipped with dual-fuel engines, it can operate entirely in pure methanol mode, enabling a one-way voyage from the Far East to the West Coast of America with reduced emissions. This innovative ship combines high capacity, advanced engineering, and eco-friendly technology, showcasing China's commitment to greener maritime transport and the future of large-scale container shipping. The LPG vessel Albert II at Lisnave undergoes precise shipyard operations, including hull inspection, outfitting, and system integration. Specialized teams handle propulsion, cargo tanks, and safety systems to ensure compliance with international standards. Advanced welding, piping, and instrumentation work are carried out with strict quality control, preparing the vessel for efficient liquefied petroleum gas transport. Each stage, from structural assembly to final testing, is meticulously monitored, ensuring the ship's safety, reliability, and operational efficiency before delivery. The manned propulsion system upgrade on the vessel B Flora in Bergen, Norway, demonstrates how retrofitting can drastically improve efficiency and reduce emissions. The process began with a thorough evaluation of the existing CP propeller, rudder, and propulsion system. The conventional propeller blades were replaced with Mann's Clee propeller design, optimized for better hydrodynamic efficiency. Additionally, a fairing bulb was added ahead of the rudder, and a rudder bulb attached to the rudder itself, streamlining water flow from propeller to rudder, significantly reducing turbulence and resistance. Hydrodynamic testing at the Norwegian Marine Technology Research Institute involved scale models in a towing tank, allowing precise calculation of full-scale fuel consumption. Comparing original and upgraded configurations showed potential fuel savings of over 20%, exceeding initial expectations. The upgrade also included adjustments to engine components and related ship equipment, offering a holistic solution rather than a single system improvement. Benefits include reduced fuel costs, lower CO2 emissions, higher environmental ratings, and enhanced market competitiveness. Close collaboration between ship owner and supplier proved essential, enabling existing vessels to match the efficiency of newer designs while contributing to sustainable shipping practices. The Port Authority's Prisma research program explores innovative dredging methods to improve efficiency, sustainability, and safety in the Port of Rotterdam. Maintaining water depth is critical for navigation, but the upper seabed often consists of silt, requiring frequent dredging. In practical trials, water is injected into silt using a rejection dredger, liquefying it and directing it toward designated harbor areas. The silt can then either settle and consolidate or remain fluid for later suction by a trailing suction hopper dredger, minimizing vessel movements, reducing CO2 emissions, and cutting costs. The program studies liquid silt behavior, effects on ship navigation, and optimal guidance using artificial or natural currents. Collaborations with institutions such as TU Delft and Deltares, and other major seaports like Hamburg, aim to develop this technology into an international standard, ensuring a safe, efficient, and sustainable harbor while supporting commercial shipping operations. Prisma demonstrates how advanced sediment management and engineering innovation can transform traditional dredging into a more precise, cost-effective, and environmentally responsible process. Trailing suction hopper dredgers are ocean-going dredging vessels designed to excavate, transport, and discharge sand and silt over long distances. They are widely used for port construction and maintenance, land reclamation, coastal defense, and riverbank protection. Each TSHD is equipped with 1 or 2 suction pipes fitted with drag heads at the lower end. Upon reaching the dredging area, the vessel reduces speed and lowers the suction pipes to the seabed. As the ship moves slowly forward, the drag head travels along the seabed, loosening and collecting sediment in a manner similar to a large vacuum system. The mixture of sand and water is then pumped on board and stored in the vessel's hopper. Dredging continues until the hopper reaches its maximum capacity, at which point the vessel sails to the designated discharge area. Depending on project requirements, the dredged material can be discharged in several ways. Rainbowing is used when the vessel can approach the reclamation site closely, spraying sand through a bow nozzle in a controlled arc. Alternatively, sediment can be pumped ashore through floating or submerged pipelines, commonly used in land reclamation and coastal protection works. For offshore disposal, material can be released through bottom doors in the hull. Through precise vessel positioning and advanced control systems, trailing suction hopper dredgers deliver accurate, efficient, and versatile sediment management for large-scale marine engineering projects. The submarine cable installation at Nordsee One offshore wind farm involves a precise, multi-step technical workflow using ISV seam Moxie and CLV seam Amory. First, pull-in, termination, and testing equipment are deployed, supported by an award-winning 3D motion-compensated crane. A pre-lay inspection survey ensures seabed readiness. The first-in pull-in uses a pre-installed messenger wire and entry hole cover, followed by surface laying, with continuous touchdown monitoring via ROV and onboard cable marker application. The second end pull-in engages the cable protection system into the foundation. Finally, post-lay trenching is performed with a trenching ROV to secure the cable within the seabed. This method ensures precise alignment, protection, and operational reliability for the wind farm's electrical infrastructure. Watch the impressive efficiency of 7-star yacht transport as 57 yachts are loaded in just 1 minute. Using advanced planning and coordinated logistics, each yacht is carefully positioned on the transport vessel. The operation showcases precision handling, secure cradling, and systematic placement to maximize space and safety. This rapid loading process highlights the expertise of the crew and the capabilities of modern yacht transport, ensuring vessels are moved efficiently and safely across oceans. It's a remarkable demonstration of speed, organization, and technical skill in maritime logistics. In Martinique, the DYT vessel Superservant 4 demonstrates its float-on yacht transport method, a specialized system for moving large yachts safely and efficiently. The yacht is carefully positioned over the submerged deck of the ship. Then the vessel is raised out of the water, using ballast control. This float-on, float-off technique allows for secure handling of yachts without cranes, minimizing risk to the hull and rigging. Observers witness the precise coordination as the yacht is guided into place, highlighting the efficiency and expertise of modern maritime transport. In Amakusa, building a boat is a meticulous, step-by-step process combining precision, craftsmanship, and advanced composite techniques. The first stage is the spray application, where the final surface of the vessel is created. A gel coat is carefully sprayed onto the mold, forming the smooth exterior. At this stage, air bubbles are strictly avoided, as they would compromise the hull's integrity. Next, layers of glass fiber are applied with liquid resin, gradually building the boat's structure. Craftsmen meticulously remove all air pockets, ensuring the material solidifies into a strong, seamless hull. The bonding stage follows, where the boat's face is created. Here, the hull and deck, previously constructed separately, are joined using precise adhesives and alignment techniques, forming a unified structure ready for outfitting. Once assembled, the vessel undergoes rigorous final inspections, checking over 130 individual points to ensure structural integrity, surface quality, and performance standards. Finally, the boat enters the pre-outfitting stage, where components like hardware, fittings, and equipment are installed before the vessel is launched. Every step, from spraying gel coat to bonding and final inspection, is executed with utmost attention to detail, reflecting the craftsmanship and technical expertise of Takemoto Shigeki and the Amakusa shipbuilding tradition. This careful combination of composite material techniques, precision bonding, and comprehensive inspection guarantees that each boat leaving the yard is both durable and seaworthy. The Big Willie crane is a specialized heavy-lift crane used annually to transfer large yachts from the river onto land for the Boot Dusseldorf Boat Show. Positioned at km 748.2 of the Rhine, it can lift objects weighing up to 100 tons. Its precision and strength allows safe handling of massive vessels, ensuring they are efficiently moved from water to display areas. This remarkable crane demonstrates advanced engineering and plays a crucial role in preparing yachts for one of the world's largest boating exhibitions. Hyperbaric pipeline repair on a live subsea pipeline is a complex offshore operation that allows structural restoration without interrupting product flow. In the Jakarta project, the repair sequence was executed under strictly controlled conditions to ensure safety, weld quality, and pipeline integrity throughout the intervention. The operation began with a detailed assessment of the current pipeline condition, including damage geometry, wall thickness, and operational parameters such as internal pressure and temperature. Based on this evaluation, suction piles were installed on the seabed to provide a stable foundation for the hyperbaric habitat. These piles were positioned with high accuracy to ensure proper alignment with the pipeline and sufficient load-bearing capacity for the habitat structure. This hyperbaric repair approach enabled effective restoration of the live pipeline while maintaining continuous operation, demonstrating a technically robust solution for subsea pipeline integrity management in challenging offshore environments. Once the suction piles were secured, the hyperbaric habitat was lowered hydraulically by divers and installation crews. The habitat was carefully positioned over the damaged pipeline section and then dewatered to create a dry, pressurized working environment. Dewatering was performed gradually to maintain pressure balance and avoid any adverse effects on the live pipeline. With the habitat stabilized, installation of the standoff sleeve commenced. The sleeve was designed to restore mechanical strength and provide a controlled welding interface around the damaged pipe section. Precise fit-up was critical, as the sleeve had to maintain concentric alignment with the pipeline while accommodating operational stresses. Welding operations were carried out inside the hyperbaric habitat under elevated pressure conditions. Specialized hyperbaric welding procedures were applied to ensure metallurgical integrity and weld consistency. Following each welding phase, non-destructive testing (NDT) was conducted, including ultrasonic and radiographic inspections adapted for hyperbaric conditions. These inspections verified weld quality, penetration, and the absence of critical defects. After initial welding and inspection, the habitat was repositioned as required by placing it securely back onto the suction piles. Lifting cables were detached once final alignment and stability were confirmed. Divers then re-entered the habitat hydraulically to continue welding activities on additional sleeve sections, following the same controlled procedures. The final stage of the operation involved the installation of corrosion protection systems. This included the application of protective coatings and, where required, the integration of cathodic protection components to safeguard the repaired section against long-term corrosion. Once all inspections confirmed compliance, the habitat was removed and the site was returned to operational status. Hydroblasting of a ship's hull is a controlled surface preparation process used to remove marine growth, old coatings, corrosion, and contaminants without abrasive media. Using the Dockmaster and Dockboy systems, high-pressure water jets are applied directly to the hull surface at pressures sufficient to strip coatings while preserving the steel substrate. The equipment is mounted on a mobile platform that travels along the hull, maintaining a constant standoff distance and spray angle to ensure uniform cleaning results. Water pressure, nozzle configuration, and travel speed are adjusted according to coating thickness and hull condition. The system integrates wastewater capture and filtration units to collect removed paint particles and residues, preventing environmental contamination within the dry dock. Hydroblasting improves coating adhesion for subsequent repainting, reduces dust generation compared to grit blasting, and enhances safety by minimizing manual work at height. Cleaning a cargo hold on a large bulk carrier, in accordance with Grain's standard requirements, is a highly technical operation that prioritizes safety, thoroughness, and structural integrity. The process takes place inside a cargo hold reaching up to 19 meters in height, where cleanliness directly affects cargo quality, vessel compliance, and operational readiness. The operation begins with a comprehensive safety assessment. All sharp edges, corners, and confined zones, commonly referred to as critical hazard points, are identified and secured. Proper access systems, fault protection, ventilation, and communication protocols are established before any cleaning work starts. Safety remains the primary consideration throughout the entire process. Cleaning is carried out using high-pressure water jets, applied from the top of the cargo hold downward. This top-down method ensures that loosened debris, grain residues, rust scale, and contaminants are efficiently flushed toward the bottom without recontaminating clean surfaces. Workers operate heavy-duty hoses and lances, directing pressurized water onto bulkheads, frames, hopper sides, and tank top plating. The cargo hold structure consists of longitudinal and transverse frames, reinforced bulkheads, hoppers, and inner bulwarks. These structural elements are carefully cleaned to remove embedded residues, rust streaks, and accumulated dust. Particular attention is given to frames, pipes, and corner sections where grain residues and moisture are most likely to collect and compromise hygiene standards. High-pressure washing effectively removes rust, scale, old cargo traces, and organic residues, preparing the hold for inspection and subsequent loading of grain cargo. Drainage systems are continuously monitored to prevent water accumulation and ensure efficient runoff. Throughout the operation, supervisors verify that all surfaces meet grain standard cleanliness, meaning they are free from previous cargo remnants, loose rust, paint flakes, and standing water. Final visual inspections confirm uniform cleanliness across vertical walls, structural members, and the hold floor. This systematic cleaning process not only protects cargo quality, but also preserves the ship's internal structure. By combining controlled water jet cleaning, strict safety procedures, and attention to complex structural details, the cargo hold is restored to a condition suitable for safe, compliant, and efficient grain transportation. APT Global Marine Services is involved in marine and offshore technical operations that support subsea and offshore projects. Typical activities include vessel mobilization, offshore construction support, subsea installation works, and inspection, repair, and maintenance tasks. Operations are carried out using established engineering procedures, method statements, and risk assessments to ensure technical accuracy and operational safety. The work often involves the use of offshore support vessels, lifting systems, and ROV-based inspection and intervention equipment. Emphasis is placed on controlled execution, adherence to class and safety requirements, and maintaining stability and precision during offshore operations in varying sea and weather conditions. In the early hours of the 14th of December 2002, disaster struck. At approximately 2:15, the container vessel Kariba collided with the Tricolor in dense traffic in the English Channel. Despite an emergency hard starboard maneuver by the Tricolor's captain, the impact proved catastrophic. The vessel capsized and sank within 30 minutes. Thanks to disciplined emergency procedures and thorough crew training, all 24 crew members evacuated safely and were rescued. However, the Tricolor came to rest on her port side on the seabed, directly in one of the busiest shipping lanes in the world. The Tricolor lay on her side, which allowed limited access to the bottom of several fuel tanks. The salvage team developed a specialized oil removal method, drilling into accessible tanks, installing valves, connecting hoses, and pumping the oil into receiving tanks. Over a period of 2 months, approximately 100 tons of bunker oil were successfully removed. Some oil remained trapped in inaccessible engine room tanks or spread across the vehicle decks, and minor leakage into the sea proved unavoidable. Nevertheless, the operation significantly reduced the environmental risk. Even as oil recovery continued, discussions began regarding the full removal of the wreck. Given the location, structural condition, and navigational danger, it was decided that the Tricolor had to be removed as quickly and safely as possible. Wilhelmsen contracted a salvage consortium known as Tricolor Salvage, comprising Smit Salvage and Mamoet from the Netherlands, along with Scaldis and URS from Belgium. Their task was unprecedented in scale and complexity. Although structurally strong when upright, the Tricolor was far too fragile in her capsized condition to be refloated or lifted whole. Engineers concluded that the only feasible solution was to cut the vessel into 9 large sections and remove them individually. 2 massive offshore work platforms with extendable legs were assembled on either side of the wreck and jacked down to the seabed at approximately 30 meters water depth, creating stable working bases in open sea conditions. For the cutting operation, the salvage team employed a specialized diamond hard cutting wire, previously used during the recovery of the Russian submarine Kursk, but never before on a vessel of this size. Extensive testing confirmed that the wire, composed of thousands of small steel cylinders coated with an ultra-hard alloy, could cut through multiple decks, internal structures, and heavy machinery. Each cut required extraordinary preparation. A flexible drilling system was used to drill beneath the wreck, allowing a hollow tube to be pulled through the seabed. The cutting wire was then threaded through this tube and tensioned between powerful winches on the 2 platforms. The wire was driven back and forth at an average speed of 1 meter per second, under forces reaching 60 tons of tension, gradually slicing through the ship's steel structure. Divers continuously monitored both the wire and the wreck, as even minor shifts in position could prove critical. Due to strong tidal currents, effective underwater working windows were often limited to just 20 minutes per tidal cycle. Once a section was cut free, divers welded and installed lifting frames and chains to distribute loads evenly. Some sections weighed over 3,000 tons, requiring dozens of lifting points. Two of the world's largest floating shear legs cranes were mobilized for the lifting phase. The first section raised was the stern, which included the engine room and was among the heaviest. Lifting operations were conducted extremely slowly to allow seawater to drain, control the center of gravity, and prevent shock loading on the cranes. As each massive section emerged from the sea, often more than 6 months after the sinking, it was carefully transferred onto a heavy barge positioned beneath it. Ballast tanks in the barge were flooded to lower its deck and maintain stability during load transfer. Once secured, the barge transported the section to Zeebrugge, where it was taken to a specially prepared scrapyard with sealed foundations to prevent soil contamination. Over time, the heaviest sections were removed first, followed by progressively smaller and more fragile parts of the wreck. Winter storms further weakened the remaining structure, eventually requiring a change in strategy. A large wreck grab was introduced to remove smaller pieces of steel, vehicles, and debris scattered across the seabed. Advanced survey techniques, including magnetometers and multi-beam sonar, were used to locate submerged cars and metal fragments buried in sand and mud. Environmental protection remained a constant priority. Anti-pollution vessels stood by throughout the operation, and French and Belgian authorities closely supervised all activities. Each recovered vehicle required certified disposal in accordance with manufacturer and regulatory requirements. By late summer 2004, after more than 18 months of continuous work, the seabed was cleared to the satisfaction of the authorities. The salvage of the Tricolor concluded as one of the largest and most technically ambitious wreck removal projects ever completed. It demonstrated not only the capabilities of modern marine salvage engineering, but also the shipping industry's ability to respond responsibly to major maritime accidents. Through innovation, precision, and perseverance, a severe navigational and environmental threat was successfully eliminated, setting new benchmarks for large-scale offshore salvage operations. The RORO vessel Tonsberg, part of WWL's Advanced Mark vs. class, represents a new generation of sustainable and high-efficiency maritime logistics. Designed to optimize global supply chains, the Mark vs. platform combines large cargo capacity with significantly reduced environmental impact. Its hydrodynamically optimized hull, featuring a bulbous bow, streamlined rudder, and ducktail, minimizes resistance while improving stability and fuel efficiency. A state-of-the-art turbo generator converts engine exhaust into onboard electrical power, saving approximately 4 tons of fuel per day and reducing sulfur and carbon emissions. Computer-controlled main engines further enhance efficiency, achieving up to 20% lower fuel consumption per transported cargo unit. Internally, Tonsberg is engineered for maximum operational flexibility. 8 cargo decks, wide internal ramps, and a 12-meter stern ramp rated for 500 tons enable simultaneous loading operations. High-clearance decks, reinforced lashing points, and dedicated heavy cargo areas allow the safe transport of oversized rolling units, automotive cargo, and heavy equipment, supporting efficient, reliable, and sustainable global trade. Transporting a 24-meter Van der Heyden Superior 2400 superyacht, weighing over 50 tons fully fueled, from the shipyard to the water, is a highly technical operation requiring specialized equipment and precision coordination. The process begins in the shipyard, where the yacht rests on a custom-built cradle to evenly distribute its weight and protect the hull. A heavy-duty transport system, often a multi-axle hydraulic trailer, is positioned beneath the cradle. Using synchronized hydraulic jacks, the yacht is lifted slightly to allow the trailer to slide into place. The transport vehicle, equipped with self-steering axles, ensures precise maneuverability through the shipyard, including tight corners or uneven surfaces. Once positioned near the dock, the yacht is slowly moved onto a floating platform or travel lift. For a travel lift, lifting straps are attached around the hull, and the hydraulic hoists gradually raise the yacht clear of the trailer. The yacht is then carefully lowered into the water, ensuring even weight distribution to prevent stress on the hull. Throughout the operation, engineers and riggers monitor structural integrity, hydraulic pressure, and alignment. Safety measures, including chocks, guide ropes, and spotters, are essential. This combination of precision engineering, heavy-duty hydraulics, and experienced personnel allows Van der Heyden to safely launch large, high-value superyachts like the Superior 2400 from the shipyard into the water with minimal risk. The GH2161 Island Flyer is a Griffon Hoverwork 12000TD passenger hovercraft. Designed for year-round service, it carries around 80 passengers, hovering 1.5 meters above the surface. With twin diesel engines, advanced hull and skirt systems, it provides fast, stable, and efficient crossings over water and tidal flats. Remote operations are redefining the way modern container terminals function. placing automation at the core of safer, greener, and more productive port operations. A new generation of ship-to-shore cranes is now entering production, featuring full remote control capability and eliminating the traditional driver cabin altogether. This shift allows crane operators to work from ergonomic, climate-controlled control rooms, significantly improving occupational health, safety, and situational awareness, while fostering stronger teamwork and communication. Automation extends well beyond the quay. Fully automated container stacks are now operated by advanced stacking cranes equipped with precision positioning systems, sensors, and real-time control software. Instead of individual crane operators, just 2 supervisors can oversee and manage the entire stacking crane fleet, optimizing workflow and reducing human exposure to hazardous environments. Automated systems handle container identification, routing, and placement with consistently high accuracy and efficiency. A key component of this transformation is automatic container landing and pickup on-road chassis. Using intelligent guidance systems, cameras, and laser positioning, containers are transferred seamlessly between cranes and trucks without manual intervention. This reduces turnaround times, minimizes handling errors, and enhances overall terminal throughput. By integrating remote operations and automation across quay, yard, and landside interfaces, container terminals achieve measurable gains in productivity while lowering energy consumption and emissions. The result is a terminal ecosystem that is not only more efficient, but also fundamentally safer for personnel and more sustainable for the environment, setting a new global standard for next-generation port operations. The GCT Deltaport Intermodal Yard Reconfiguration Project is designed to meet the growing demands of modern marine transportation. The reconfigured rail yard, completed in April 2017, integrates high-efficiency equipment, dual railway access, and advanced automated systems to reduce dwell time and increase service velocity. By separating mobile equipment from trackside operations and using remote crane control and auto-decoupling zones, the terminal can operate 24/7 safely and efficiently. The expansion increases intermodal capacity by over 50%, supporting transcontinental rail partners CN and CP, enabling faster deliveries to destinations across Canada and the U.S. Midwest. This modernization reinforces GCT Deltaport's position as a premier North American terminal and ensures continued high productivity, service certainty, and supply chain efficiency through the Asia-Pacific Gateway. At the St. Louis-Arzviller Inclined Plane, engineering and ingenuity converge to move boats with remarkable precision. The massive, counterweighted caissons glide along the incline, guided by steel tracks and balanced by a complex system of cables and pulleys. Water levels are equalized within the caissons, allowing vessels to transition smoothly between different elevations. The rhythmic hum of motors, the creak of metal, and the gentle splash of water accompany each operation. Tourists watch in awe as boats ascend or descend the 44.5-meter slope, a testament to 19th-century hydraulic engineering still fully operational today, blending functionality with a spectacular display of mechanical mastery. The Elblag Canal comes alive with the sound of rushing water and the rhythmic clatter of a mill wheel in motion. Ropes transfer energy, gears turn steadily, and a large boat emerges on a metal cradle. The wheels grind along the tracks as the vessel climbs the inclined plane. Defying gravity and logic, the boat appears to glide over grass. Dozens of onlookers from the shore and aboard the vessel watch this mechanical marvel in action. This is where engineering meets wonder. An extraordinary journey begins on the historic Elblag Canal, showcasing the ingenuity of canal transport.